All right, let's have a look at practice question set 2A. Question number 1 says the physical quantity that can have the same unit as impulse is what? Unit, by the way, means like what it's measured in, right? The units for speed would be meters per second. The units for impulse, either kilograms meters per second or Newton seconds. What has the same units as impulse? Quick. Momentum. Yeah, good. The answer is D for that one. This airbag, this question says, airbags are designed to deploy when a car moving at a minimum speed of 18 kilometers per hour comes to a crashing stop. The impact sensor, also moving at 18 kilometers per hour, consists of a small steel ball of this mass, held in position by a magnet. On impact, the ball breaks free in a very, very short amount of time, goes within a cylinder, and then makes contact with two electrodes, completing a circuit, which what that ultimately does is applies an electric current through this powder, produces a chemical reaction that generates a gas, and inflates the airbag. And it all happens incredibly quickly before your head comes to hit the airbag. We want to know the magnitude of the force required to break away from the magnet. This is a little bit tricky, actually, this question. Okay, this one's a bit tricky. We're going to say for this one, this is an impulse question. An impulse question. We know it's an impulse question because we see force and we see time. If you look at the backboard here, I've got under our always list that started, force and time lead us to impulse. Okay, that's what we do. We see force and time in the same question. We go straight to impulse. So that's what we're going to do here. But we're going to write down our givens first. We're going to say the mass of this steel ball is 0.050 kilograms. We're going to say that the I is, the F is, this is the tricky part. If people look at this and say, well, the ball's moving at 18 kilometers per hour before this collision took place, how fast is the ball moving after the collision took place? 18 kilometers per hour. Well, then that's no impulse, right? Relative to the ground, that would be true. But relative to the car, how fast was it moving relative to the car before the collision took place? Was it? 0. The car was moving at 18. The ball was moving at 18. The car and the ball weren't moving relative to one another, right? So we're going to say VI relative to the car, VI is 0 meters per second. Now VF, after the ball is released, the car is now stopped. The ball is moving at 18 kilometers per hour or 5 meters per second. So I'm going to say VF is 5 meters per second. Does that make sense, you guys? We can't define it relative to the ground because there is no impulse relative to the ground. The ball remains moving at 5 meters per second. It was moving at 5, still is. There is no impulse. But relative to the car, on another frame of reference, there is an impulse because there's a change in velocity. My time interval is 1.00 times 10 to the negative 3. You guys know that you can use F times T, you can use M times delta V, or you can use the combination. I'm going to choose to use the combination here. Rearrange that to solve for F. You get M times delta V over T. What do we got here? 0.050 times delta V, which is 5 minus 0, over delta T, 1 times 10 to the negative 3. Oh, here, I'm going to do this on the calculator, okay? Because some of you are going to make a mistake, not with the math, but just on your calculator entry here. Here's what lots of you will have done. 0.05 times 5, because 5 minus 0 is 5, right? Divide that by, some of you would have done this, 1 times 10 to the negative 3. I don't know what it is with you guys. It's not just you guys. It's every student through the history of TI calculators. Enters it this way. Don't do it this way. Do it the way Jacob did it. Okay, that's the right way. This gives you the wrong answer. If you do it this way, 0.05 times 5, and then divide that by 1 double E, okay, second function, double E, negative 3, that gives you the right answer of 250. Okay, here's what happens, guys. Your calculator, when you do it the second way, puts the 1 and the 3 together. When you do it the first way, it says 0.05 times 5 divided by 1, and then it multiplies the whole thing by 10 to the minus 3. So do it the second way. Do it Jacob's way. Okay, we should call it from now on Jacob's way. The answer is 250, which means the answer is C. Man, don't make this harder than it has to be. Don't make this one harder than it has to be. Car is moving at 18, comes to a stop. How fast is the ball moving? Keeps moving, right? It could slow down a little bit because the magnet could kind of hold it back a bit. But what's the maximum speed that it could be going? If it was moving at 18 with the car and the car stops, what's the maximum speed the ball can go? 18. So the answer is what? B? What is it? C, because it's 18 kilometers per hour or 5 meters per second. Don't get tricked by that. Get tricked by that dirty, rotten trick that they tried to pull on you. 4 is real similar to number 2, probably a little bit easier actually. We're looking for the force here. Once again, it's delta P over, we're going to say M times delta V over delta T. It's just Ft equals M times delta V rearranged. We know this is 70. Delta V is stops, so 0 minus 5 meters per second over 0.10 seconds. Can't remember what the answer was for that one. B is our answer. 3.5 times 10 to the 3 newtons. Number 5. The entire process from impact to airbag inflation takes less than 3 times 10 to the negative 3 seconds. That's how quick it is. How far forward would a passenger who is not wearing a seatbelt move? Sorry? Well, then you're going to pick C then, right? No, farther. Okay, well, if you don't think the person is going to go through the windshield, which is not a very good airbag if the person goes through the windshield before the airbag inflates, that means the answer is not going to be C, right? What else is the answer not going to be? 0. It's not going to be 0. The person's going to move forward, right? A or B. Let's not make this harder than it has to be. How far forward does the person move? How fast is the person moving? Car was moving at 5, so is the person. Now the car stops. The person not wearing a seatbelt keeps going at 5 meters per second. Who said that? Me. There you go. What a genius. Always look over to Jacob. He's got the answer. It is Newton's first law. Object in motion keeps going in a straight line at the same speed until the airbag stops it. Or until the seatbelt stops it, right? Or until the windshield or the pavement stops it.